All right, we're going to talk about the energy in ionic bond formation. This is going to pull in energy concepts from back in chapter 6 with delta H values and again, ionization energy and electron affinity, which we talked about in chapter 8. So the ionization energy of a metal is endothermic. See, we have a positive delta H value. The electron affinity of a nonmetal is exothermic, but it's not as large as that endothermic part. And that's typical. The ionization energy of the metal tends to be larger than the electron affinity of the nonmetal. But the heat of formation of most ionic compounds is generally large and exothermic. So there's some part that we're missing because remember, delta H is a state function. And so our numbers should add up and we're missing something. The thing we're missing is the formation of a crystal lattice, that lattice energy. In a crystal lattice, there's no direct anion-cation pair. It's every anion is surrounded by cations and cations are surrounded by anions. And so a lot of energy is given off because of the amount of positive and negative charges that are brought in close together. So that extra energy given off is called the lattice energy. One way to calculate the lattice energy is to use the Born-Haber cycle. This is using Hess's law, and it adds up the enthalpy changes of other reactions to determine the overall lattice energy of the formation of an ionic solid. So we can look up the delta H of formation of the salt. We can find the delta H of formation of putting the metal ions into the gas phase, the delta H of formation of bringing any nonmetal atoms to the gas phase, the delta H of formation of the cations, which is going to be your ionization energy, plus the delta H of formation of the anions, your electron affinity, plus the delta H of your crystal lattice will be equal to your delta H of formation of your salt, so you can back calculate this lattice energy. So for a metal atom, to go to the cation, your delta H of formation is going to be your first ionization energy. If it goes to the +2 state, you have to add together the ionization energies for taking away the first electron and the second electron. Then for nonmetal, your delta H of formation is your electron affinity. So let's look at a picture of this. Sometimes I think that's easier. So we're going to start here at 0 with everything in its standard state, so solid sodium and chlorine gas. Then in our first step, we're going to break apart our sodium atoms into gas molecules. Again, this is all theoretical, just to get all the steps that we need. Then we're going to break apart our chlorine atoms, which is going to involve some energy being added. Then we're going to use our ionization energy to figure out how much energy it takes to go from sodium to the sodium ion. Then we're going to get some energy back. This is going to be our electron affinity by giving that electron over to our chlorine. Then when we bring our two parts together, we end up with our lattice energy. That's this kind of burgundy arrow. And then overall, our enthalpy of formation is what it takes to go from our standard states to our product, our sodium chloride. So that's this purple arrow here. So we can break it up into the individual steps and solve for number 5 there if we don't know it. Now there are some trends in lattice energy size. The force of attraction between the charged particles is inversely proportional to the distance. So the larger the ions involved, the weaker the attraction. And the weaker the attraction, the smaller the lattice energy, because those charged particles just can't get as close together. And it's charged particles coming together that gives you the lattice energy. So here's an example, lattice energy versus ion size. So our anion is chlorine the whole time, chloride. And we can see that our lattice energy decreases as our atomic radius increases down the periodic table. We get less energy out. So let's work through an example. Order the following ionic compounds in order of increasing magnitude of lattice energy. So here I would compare, so we're going to compare our potassium bromide to potassium chloride. Then we're going to compare our calcium oxide to our strontium oxide. Then we'll think about what order they should be in. And we're going in increasing overall. So potassium bromide versus potassium chloride. Potassium chloride is chloride is smaller than bromide. So if we're going in increasing magnitude, potassium bromide is less than potassium chloride. Over here, calcium oxide, strontium oxide. Calcium is above strontium, and so strontium oxide is going to be less than our calcium oxide because calcium oxide has the smaller ions because it's higher on the periodic table. Then here we're looking at charges of +1. Here we're looking at charges of +2. So anything with a +2 is going to be more attracted to each other. Which means here's our overall order. Our calcium oxide is going to have the largest magnitude of lattice energy. So there we go. Next question, which of the following compounds will have the highest magnitude lattice energy value? These are all bromide compounds. So potassium, sodium, lithium, or rubidium bromide. The highest magnitude is going to be the smallest radius. And out of those, the answer is lithium. Okay, ionic bonding. Model versus reality. So Lewis theory does pretty well in predicting how ionic compounds behave. So Lewis theory, we've talked about how those positive and negative charges attract each other. Those are strong attractions, and they should have high melting points and boiling points because of those strong attractions. And in order to break all of that, you have to break that lattice energy that we were talking about. So our prediction is that ionic compounds have high melting points and high boiling points, which ends up being true. Melting point is greater than 300, and they're all solids at room temperature. Lewis theory would imply that the positions in the ions are critical to the stability. So it's the positive and negative charges interacting that allows for the stability of the crystal lattice. So moving those ions out of position should be difficult, which means they should be hard. The way we measure hardness is by rubbing two materials together and seeing which one streaks or cuts the other one. And if you compare ionic solids to most molecular solids, the ionic solids are typically harder. If we displace ions, then we should get some repulsive forces, which should allow them to break apart. The word for that is brittle. And if you imagine taking a piece of salt and hitting it with a hammer, it shatters. The reason is because then, my graphic here doesn't work, but it shifts so that two positive charges are next to each other and negative charges are next to each other. So that's going to break apart along this plane because same forces repel each other. And then conducting electricity, we need charged particles flowing through. And because our ions are locked in position, they should not conduct electricity in the solid state, which is true. But when you dissolve them in water, we get ions floating around, which allows for electricity to move through. So either a liquid ionic compound and those dissolved in water conduct electricity. And so here you can see, here's a block of salt, does not conduct electricity, but when you dissolve it in water, the ions can move around and we get electricity flow through the solution, and that lights up the light bulb.